and the kind of renormalizable one. So why this is kind of suppressed compared to and what one value. We can do this with the factor operator language, and there also, depending on whether you use a 45 fix here or a 5, you can get either a value of 9 halves or a value of 6. And if you go back to the data, actually, this value 4.4 is close to 4.5, which would be 9 halves. So this would fit also quite nicely. So we have a few interesting possibilities, a few interesting predictions here for this quark-lepton mass ratios in SO4, which, so this here would work even without any corrections within the errors that we have from the equivalent at the moment. These here need to have corrections in two different directions. So one could also be able to distinguish if you would have measurement. So when you want to construct a quantum unified theory, these are kind of choices you have to make. You have to choose operators which generate your cover matrices. You have to choose field representations. So you have to, this is a very big constraint because the measurements, especially for the quark masses for the first two generations, become better and better. So you really have to see that you get models which predict the right values. And in the future, when we will test this, maybe we can find out in which kind of models are going in the right direction. Okay, so which ratio is consistent? It any depends on the SUSY model parameters, and we hope that you will measure that. But in a constrained MSSM, it would go in the direction of 3.5 or 6, or 9.5 would also work if the special corrections are small. But yeah, as I said, in order to test this, we really have to measure which corrections are there at TD scale. Okay, this is just the overview. What we did, so we were going here from the Stellar model to the minimal electron model to the Partisalan model up to SO10, which you can view as the mother of quantum unified theories in some sense. It's the bigger group. And the SO10 you could also, if you like, break to the SU5 gauge group. So this is the other case. Here you're no longer left-right symmetric. Here you're following the left-right symmetric path, which means you're predicting a right cardinal neutrino in your spectrum automatically. You're more driven towards a type 1 plus 2 or Q type 1 Caesar mechanism. Here you have the choice to realize type 1, type 2, or type 3. Okay, so these are the implications. Guts for neutrino masses. Do we have at some point some questions? I have something else prepared. How much time do I have? 15. Yeah, 15 minutes, sorry. So do you have some questions so far about what the guts?
Yeah, how do you test it experimentally? We only live in this lower scale. So experimentally can only measure that use the rough coupling to
okay, so what you can test when you think of the label parameters, like the Fermion masses in mixing and so on. So I think in general, the only thing that you can really test is a carefully constructed model. A model which basically has normally that kind of extra symmetries, not these symmetries like this here. It has extra symmetries, which are, for instance, telling you which of these standard model Higgs representations are coupling to which matrix element, for example. Yeah? And if you have a fully constructed model, then you can derive its prediction. You know which are the free parameters, and you can test it. So this is when you want to talk actually about this mass ratios. That's all. So you would have to construct a full model. You also have to know your theoretical uncertainties in these predictions, and then you may test it. So we have constructed recently some examples of models which are very predictive, and did a careful study also what are the uncertainties and what do we exactly predict. So this, yeah, was a kind of some recent works with my group. There's something else, of course, which is kind of the smoking gun of quantum unified theories in general, which is the decay of the proton. And this would be kind of an extra chapter, which I cannot open here, really, because I wanted to specialize on the connection to neutrinos. But kind of the decay of the proton would be something which would be a very good indication for a quantum unified theory. And you would not see this in the standard model, but you need some extra ingredients. Guts generically give you rise of proton decay. It's also a bit model specific, especially in supersymmetric theories, and there are also some interesting constraints coming from this. But I think we don't have time to really expand on this. If you want to discuss later, we can also discuss about proton decay. But that would of course be fantastic, and the experiments are continuing to look for it in their new proposals. Yeah, maybe this is the next big discovery. That would be small enough for us. Yeah. Okay, so then let me continue. So last thing I wanted to mention is that in any model of this type, also when we have a neutrino model, or especially when we have a neutrino model, what you should include also is the renormalization running carefully in this kind of model. And especially when you have a Caesar model, this requires you to go through various effective theories and consider also carefully the matching of these theories. So you start with your model as we discussed it, defined at the grand unification scale here. And in order to get neutrino masses of the right size, very typically you have your right-handed neutrinos, which may be 3. So from the present data it have to be only 2, but in grand unified theories, like the left-right symmetric grand unified theories, you predict that there are 3 of them, so 3 partners of the left-handed neutrinos. And in this theory here, you have to run your mass matrix of the right-handed neutrinos and your cover matrix of the neutrinos up to this energy scale. So you solve the renormalization group equations up to here. Now when you are at this scale here, you have to re-diagonalize your mass matrix of the right-handed neutrinos. You have to integrate out the one which corresponds to this threshold here. That's at least the cleanest way to do it. Then you reduce your neutrino cover matrix here to a 2 times 3 matrix. You continue running here in this theory with the reduced cover matrix. You have a 2 by 2 right-handed neutrino mass matrix, and you're generating already here a contribution to an effective 5 neutrino mass operator. So to this operator. So in addition, you have to also compute the running of this dimension 5 neutrino mass operator. And then the same thing you do at this threshold and at this threshold. And then just below here, you only have to calculate the running of this dimension 5 neutrino mass operator. And this is really important to calculate also the neutrino predictions when you come from a high scale, like from a grand unified theory. And we have a software code which is called Weak, which you can find when you go to this paper here in the comments, and you can find a link to the website, which is doing this for you kind of automatically. But that's something, so you just plug in your matrices here, and it can do the complete running of all standard model and neutrino parameters, including the thresholds carefully, from the gut scale to the electric scale, if you like. That's something important. So why is this important? Okay, here's the beta function for the RGEs for the kappa operator. So that's the operator here for the effective operator. And this here is basically how it is running. The running depends on charge left and cover matrices, traces over the Borg cover matrices, on the gauge couplings, and so on. So it's not easy to see what's going on with the parameters. But in order to do this, we also did something which is helping. This is we derive the renormalization group equations for the mixing parameters. And here you can see nicely under which conditions something happens, and you can also use this as a first estimate. For example, here you have the theta function for the mixing angle theta 1, 2, which is proportional here to the factor, the W carbon coupling mainly, the mixing angle themselves. So the fact that we have large mixing here means that this mixing is also larger in the neutrino sector compared to the quark sector where the mixing is small. We have here the ratio of the masses over the delta m squared. Okay, so this means, and we have here some phases. So it depends. So if this here is kind of, if this running is large or small, it depends. In the first place, if this mass scale here is big, so if you are in the quasi-degenerate limit, where the masses are much bigger than the mass splittings, then this factor here becomes very large, and you see that also the renormalization group running is very large. So this is the first situation when you come to quasi-degenerate neutrinos. These here can really have huge effects. So it can change the mixing pattern completely. You can run from small to very large mixings. Basically everything can happen. The next comment is that you can see it depends very much on the phases. So you can also cancel this contribution to the running if you have here phases that are different by pi. And because then if the masses here, even if the masses become similar, so quasi-degenerate, you can have a negative sign here, which is again suppressing this randomization group running. So also the phases are very important. And then of course it depends on the size of the carbon coupling. So it is particularly in the MSSM when you go to large value of term beta, then the carbon couplings get bigger, and also then the randomization is running, is becoming important. And this is just basically, if you want to really calculate carefully between the predictors in a CAD model, so this running can be important if one of these conditions is fulfilled. In any case, for a precision analysis, it should be included, even for basically smaller neutrino masses and for any situation. Okay, so yeah, these are basically the 3 comments that I just made. And I think also that's all I wanted to tell you, so we can now move to the discussion if you have any questions.
We have time for your question.
When you talk about the rounding of the neutrino mixing matrix, something like that, does the phase of a charged lepton quarks affect the rounding?
The phase?
The phase of a charged leptons.
The phase of the charge leptons.
Well, what's the role of these phases play in the rounding of a neutrino, let's say, mixing matrix?
Well, what you have is the PMNS matrix, so the leptonic mixing matrix. And these phases, this is something where these formulae here are very kind of helpful. I think maybe I didn't explain this very well. So you can see here in this formulae, you can see the mixing angles of the PMNS matrix, and you can also see the phases of the PMNS matrix. So the phases, I probably should have explained this better here. These alpha 1, alpha 2, these are the Majorana phases. So if you kind of remember the parameterization of the PMNS matrix, it's like in a quark sector, we have this complex 1-3 rotation. So this is the Dirac CP phase in the lepton sector. So this Dirac CP phase is this delta here. Or it also appears kind of here. But in addition, we also have these Majorana phases, since we have here a Majorana neutrino mass matrix. So we have a type 1 Caesar mechanism, this means Majorana neutrinos. And then on the right side, there's a diagonal mass matrix. There's a diagonal matrix which has 2 phase factors. And these are the alpha 1, alpha 2. These are the so-called Majorana phases. They also CP-validating phases, which would not be there for Dirac neutrino masses. These are only there in physical for Majorana neutrino masses. They do not appear in neutrino oscillations, so at the moment we have no knowledge of them. A combination of them appears also in the effective mass for neutrinos called beta decay. But well, at the moment we kind of don't know them. They can be predicted in specific models, but these here are these alpha 1 and alpha 2. So you can see here, for example, that's what I tried to explain for the running of theta 1, 2. So you have, and if you go to almost degenerate neutrino masses, so neutrino mass is much larger than the mass splitting, then you would expect here, for example, a very, very strong running, because this here is much bigger than the denominator, so you have an enhancement by this factor. However, if there's a difference of pi in these Majorana phases here, this again suppresses this randomization group running. So the phases are extremely important. And you can also see that the phases appear here in the formula for the running of the theta 1-3. So, yeah, here is also a phase, the alpha 2, which appears in the running of theta 2-3. So they are really very important. And they determine if such a neutrino pattern is more stable or more unstable under the randomization group evolution. And you can understand this by working with this formula. And so I think phases are very important. And also the phases themselves are evolving under the randomization group evolution. So I have not shown here the randomization group equations for the phases, but you can also find them, for example, here.
Still have time for another questions?
So, you have some flavors which predict the direction of the So can we say that these are related to the gas speed and Caesar threshold corrections can
I will come tomorrow in my last lecture on the kind of family solution part and also kind of model building for the but since we are here already with the randomization running, when you look at it formally, then you can see that there is basically no. Well, I think it's also easy to see this directly from here, but you can look at it's not so easy to really just increase the value of θ13 without changing some of the other values of the mixes. So you can try to play with phases, but as far as I can think, it's not easy to only increase θ13 but leave θ23 and θ12 almost unchanged. I think what you can generate a large θ13 also by randomization of running, of course. Yes. So I think also kind of below the scale, you could probably do this if you have crazily generated tree analysis. So that's also an interesting possibility. Yeah, for example, if this Boss experiment, which I already mentioned in the last lecture, has this indication of the sum of the tree analysis equals 1.3, then you would be in the crazily generated regime. Then randomization of running can really change everything. So it's very enhanced because of the factors that you have here. So masses over mass splittings, or masses over mass splittings, these can become very big and can have a very large value, which will of course also make it more difficult in some sense to extract the information. But you can compute this running quite reliably, so it's not a big problem.
Okay, we still have the third talk tomorrow morning, and we have plenty of time for further discussion. Okay, so
Yes, if you have any questions, just find me to contribute.